Swayam Prabha. Digital India. Educated India.
Good morning. In the last lecture, we studied numerical methods for solution of ordinary differential equations, in particular the initial value problems. In the initial value problem, at one value of the independent variable, all the components of the dependent variable vector y is given, and that signifies an initial value problem. We will have quite a few further issues to discuss in the numerical solution of initial value problems, but today's lecture, let us start with a brief introduction to the boundary value problem, after which we will return to the advanced issues of initial value problem. So, let us start with boundary value problems. From the initial value problems to boundary value problems in differential equations, there is a complete paradigm shift, which can be visualized with the help of these two questions. Suppose we ask this question, that is, a ball is thrown with a particular velocity. Velocity means speed and direction combined. So, a ball is thrown with a particular velocity at an instant of time. What trajectory does the ball follow? That is, in future, what will be the trajectory of the ball? That means, at the starting time, all the conditions are given, the complete state vector is given, position as well as velocity, and we want to know the position and velocity in instants of time in future. This is a typical initial value problem. Correspondingly, and in contrast, a typical boundary value problem will look like this. How to throw a ball such that it hits a particular window at a neighboring house after 15 seconds. That means, at time 0, we know the position, we have to throw the ball from here, and at time equal to 15 seconds, we want a particular position. That is, the conditions are given half at this time instant and half at a future time instant. So, at the initial time, we are giving only the position and not the velocities, that is asked how to throw a ball. On the other hand, at the end point, we are giving the position, that is position at this point and position at that point. So, this signifies a boundary value problem. Now, this is a difficult problem physically as well as computationally. Physically also, you can consider this issue, that if you want to target a particular window where the ball goes exactly after 15 seconds, for that you need to make a very detailed preparation, and possibly you have to try 1 or 2 times before perfecting the speed and direction. On the other hand, for the first problem, physically all that you need is a sophisticated measurement mechanism, by which at every time instant you will go on taking the snapshots of the ball. Now, physically also this is a more tractable problem, comparatively this is more intractable. Computationally as well, we will find that solving boundary value problems will require more iterations and will require greater computational resource. A particular case we will discuss here, which is called a 2-point boundary value problem, the kind of problems that is illustrated by this question. So, in this kind of boundary value problems, the conditions are given at 2 points, 2 values of the independent variable, as here. So, boundary conditions at 2 values of the independent variable will signify a 2-point boundary value problem. The number of conditions could be dispersed even at more than 2 points. For example, we could have given some position at one time instant, some other positions at another time instant, some velocity values at another time instant, that is also possible. So, a specific kind of problems involves 2 points, typically at the 2 endpoints of the domain. So, that constitutes boundary of the domain, and that is why it is a boundary value problem. But in general, boundary value problems could have conditions given at various points, but we will consider here this class of problems called 2-point boundary value problems. So, the methods of solution, one is shooting method, which is conceptually the easiest, and then you have finite difference methods, finite element methods, and so on. So, we will consider two methods here, one is shooting and the other is relaxation or finite difference method. In the case of shooting method, let us understand it with the help of an example. Suppose at x equal to a, we have got some values given, and at x equal to b, we have some other values given. Okay. Now, let us consider a problem in which the differential equation is this, where y is 5-dimensional. Okay. That means, let us take y1, y2, y3, y4 and y5 be the state variables. Now, at x equal to a, these are the values. If all these values, all these 5 values at x equal to a are given, then it would be an initial value problem. Now, in this particular case, suppose at x equal to a, all values are not given, but then at x equal to b, some values are given. Total, how many conditions we need, how many values out of 10 values, how many values we need to consistently solve the differential equations? We need 5 values out of these 10 values, right. So, for the 5 values, suppose at x equal to a, y1 is given, at x equal to b, y2 is given. That means, the value of y1 is given at x equal to a, the value of y2 is given at x equal to b, then value of y3 is given again at x equal to a, and value of y4 is given at both ends, and value of y5 is given neither at this end nor at that end. That is possible. So, a total of 5 conditions are given. Now, from these 5 conditions and from this differential equation, we want to solve the differential equation, solve the boundary value problem over this domain, right. Now, we make this observation that if we knew these 2 values also, then it would be so nice, we would solve it as an initial value problem, right. So, suppose we make a guess of these 2 values. So, say we take P1 as this value, which is not given. Similarly, another guess if we make, which is this value, which is also not given, y5, right. The 2 values at a which are not given, for that suppose we make some guess. Okay. It is like trying to hit the target, we try to make a guess of the direction and then shoot it. Similarly, we try to make a guess of y2 and y5 at x equal to a and solve the initial value problem. Solution of an initial value problem is equivalent to pulling the trigger and letting the bullet go. So, as the bullet goes, typically first round it does not hit the target, it goes somewhere else. What is meant here by saying that the bullet does not hit the target? It means that the positions which are prescribed at the end point, they are not correctly achieved. So, that means with these guesses of y2 and y5 at equal to a, the point in the state space where we reach from that point we can work out, we can figure out y1, y2, y3, y4, y5 at x equal to b, and we find that at these 2 points the value does not match. At these points whatever is the value we do not know, the true value we do not know. So, there is no way to match these 2 values, what it should be we know, and where we have reached that we get from the solution of the initial value problem. So, between these two we can work out the discrepancies. First error is error in this. So, with these guesses for the 2 unknown state variable values at equal to a, with these guesses for them, the initial value problem that we have solved gives the value of y2 here as y2 tilde, and the true value is this at b, right. Similarly, the other value that is known, for that also we can find out the error. Right. Because of our specific choice of these 2 values, we have got these 2 specific values of errors. Right. Now, the question boils down to finding out the suitable values here such that these 2 errors are 0. In a typical target hitting problem, what we do after we find the error, that is compared to the bullseye, whatever shift we have made in our first attempt, we make an estimate of the direction change that we should give to the gun, so that next round it hits the target correctly. Accordingly, we change the direction of the gun and hit again. So, that means the initial condition whatever was assumed was slightly erroneous, we try to make a correction in that, right, and corrections should be made in such a manner that eventually these errors turn out to be 0. Now, note that with small changes in P1, P2, there will be small changes in E1, E2, right. So, that way we can consider E1, E2 as functions of P1, P2, and then try to solve this system of equations. In this particular case, this system of equations is actually a system of 2 equations, E1 equal to 0 and E2 equal to 0 in 2 unknowns P1 and P2, right. So, we can try our standard Newton-Raphson method for solving these 2 equations in these 2 unknowns, and for that we will need the Jacobian. Jacobian means derivative of these 2 errors with respect to these 2 variables. That means a 2 by 2 Jacobian matrix we will need, and for that we need to give small change to P1 and small change to P2 and register whatever is the differential change in E1 and E2, and accordingly build the Jacobian matrix. Now, that means that for every iteration after solving one initial value problem, in order to find the Jacobian, we will need to solve 2 more initial value problems, one with a little shift in P1, another with a little shift of P2 at P2 at P2. So, then with so many initial value problem solutions, we will get the error value at the end at these 2 values and its Jacobian, its rate of change. Based on that, we can apply one Newton-Raphson step, one correction, and this can go on iteratively, eventually hopefully converging to E1 equal to 0 and E2 equal to 0, which will mean that now we have converged to the correct values of P1, P2, that is correct values of these 2 state variables at the point x equal to a, and the corresponding solution of the initial value problem then will be the correct solution of the boundary value problem as well, because initial values are matched and final values have 0 error. So, this is the theme of shooting method, that is you make trials to shoot the target, these 2, and depending upon error at every iteration you try to change the initial values and accordingly try to perfect step by step your attempts. Now, here we took a simplified case in which 3 values were given. It could be somewhat more general, rather than giving 3 values at this point x equal to a, there could be 3 relationships between all the 5 values. Similarly, here rather than giving 2 values, it could be 2 relationships among 5 values. Okay. Then also conceptually the problem remains the same, because in that case if there are 3 relationships between these 5 variables, then we can find out 3 parameters, or rather 2 parameters, in terms of which these 5 can be expressed. Those 2 parameters will be P1, P2, because 5 variables, 3 equations will mean 2 choices in our hand. So, in terms of 2 parameters P1 and P2, we could express all the 5 unknowns or 5 variables. So, in general the shooting method will look like this. It will follow the strategy to adjust trials to hit a target. Now, in a 2-point boundary value problem, where this is a differential equation and there are a few relationships given among the state variables at x equal to a and another few relationships at x equal to b. Now, the number of this, let us say it is n1, and the number of this dimension of G2, suppose that is n2, okay, then n1 plus n2 must be equal to n, because if the dimension of the problem is n, if the state space is n dimensional, then we will need n conditions. Less than n will not be enough, more than n may be inconsistent, right. So, in that case what we do, with the help of these n1 equations, we parameterize y of a as a function of n2 parameters, that is n minus n1, this is n2 parameters. So, n2 values p1, p2, p3, p4 up to pn2. Okay. So, n2 becomes the dimension of p. Okay. So, in terms of those n2 variables, we parameterize y at this end, right. Now, if we make choices for these n2 values, then we get a complete state vector at x equal to a. With such guesses, with n2 values of p, we make guesses and then we define the initial value problem. Same differential equation and y a completely given, right, with these n2 guesses of p made, p1, p2, p3 up to pn2, right. Now, this initial value problem can be solved over the interval a to b, and we can evaluate y of b, and then we try to put this y of b into this equation, right, and that will give us n2 equations, which we try to solve. So, error vector is this, and we try to solve EP equal to 0. So, that means that for the solution of this system, from the current vector p, n2 perturbations having perturbation components in the E1, E2, E3, E4 directions, that is coordinate shifts, we can evaluate the Jacobian matrix. That means that each Newton-Raphson step will require solution of n2 plus 1 initial value problems, one for getting E of p and another n2 here to evaluate the Jacobian. After that, we can execute one Newton-Raphson iteration, which is next p is equal to current p minus that Jacobian inverse into current error, right. So, this is the typical Newton step for this problem. So, shooting method, this method has the advantage that it requires very few parameters to start with, only n2 variables we have to select and then we can start shooting. On the other hand, the disadvantage is that there is no guarantee of convergence, and the problem is very sensitive to the working of the method is very sensitive to the initial guess. That means, initial guess becomes very important. If the initial guess is far away, then the iterations may go anywhere, and that is a typical drawback of Newton's method. On the other hand, it is a good method to start with, that is, if you have a problem for which you need the solution, it is a good idea to first try shooting method quickly. If it works, you have your solution in hand. On the other hand, if it does not work, then a more sophisticated method can be tried, which is finite difference method. Finite difference method adopts a global perspective. So, for this same problem, let us see how a finite difference method will work. In a finite difference method, first we will discretize this domain. Let us say for the time being that we are discretizing this domain A to B into 8 steps. Okay. So, 8 intervals. This is x0 and this is x8. This is x4, this is x6, this is x2, this is x1, x3, x5, x7. So, there are 9 values of x. Okay. N is 8 and there are 9 values of x starting from x0 up to x8 and 8 intervals. Okay. x0 to x1, x1 to x2 and so on, 8 intervals. Now, if we do that, then what we can do, that for every interval we can write this differential equation in discrete form, right. So, then from the differential equation we get what is called finite difference equation. So, for example, suppose at x3, if this is the value of y, now here I am showing y directly along this axis, but actually that is not a one dimensional entity, that is a 5 dimensional entity. Okay. So, suppose the vector y vector at x3 is something and at x4 it is this. Now, the differential equation written for this interval, at what point we write the differential equation? Suppose we try to write it in the at the midpoint, then it will look like difference in y, that is yi minus yi minus 1, difference in y is equal to dy by dx, which is this, into difference in x. H here is x8 minus x0 by n, right, or b minus a by n, and this is same as xi minus xi minus 1. Now, this f evaluated at which point? We are planning to evaluate it at the midpoint. Okay. So, that will mean xi plus xi minus 1 by 2 yi plus yi minus 1 by 2. So, now consider this. This is an equation in xi minus 1, yi minus 1, and that is it, right. You can also say you bring the entire thing on this side and okay. How many equations are here? Y has a dimension of 5 in this particular problem. So, actually you have got 5 equations here. Five equations here, and like that you will get 5 equations over every interval. So, that means into 8 intervals are there. So, you will get 40 equations. 40 equations you will get in these variables. The variables, the unknowns involve the values of y, values of x are known, right. So, unknowns involve values of y. So, you have got 40 equations, and how many unknowns are there? There are 9 points, at each point there are 5 unknowns, that means 45 unknowns. 45 unknowns, 40 equations, 5 equations less. Those 5 equations you get from here 1, 2, 3, 4, 5. 5 conditions are given. So, 45 equations in 45 unknowns you can solve. Now, there are 2 issues. If the differential equation is linear, then this will be a linear function of y, right, and that means that this system of equations that you get from here will be a linear system of equations. On the other hand, if the differential equation is non-linear, then you will get a non-linear system of equations, and for solving them iterations will be necessary. This is one issue. Second issue, is, of course, in the first issue, even if the differential equation is linear and the resulting algebraic equations that you get out of this are also linear, still iterations could be used, and at times iterations are found useful, and relaxation method typically uses such iterative methods like Gauss-Seidel method or Jacobi method to solve the linear system. Now, if the system is nonlinear, then if the differential equation system is nonlinear, then this algebraic equation system will be nonlinear, and the iterations will be necessary. You cannot solve it in one step. So, you have to use iterative methods, and for that purpose you need Jacobian. Now, one good point here is that the finite difference equation that you see here will involve variables only from here and here, not from here, not from here. That means, every bunch of equations like this, every bunch of 5 equations that you get from here will involve only a few variables which are close by in around this interval, right? And that means that the Jacobian that you will get out of it will be sparse, and here you will take advantage of the sparsity of the matrix, and you will use those kinds of methods which work well with sparse coefficient matrix for solution of linear system. Now, let us see the outline in a generalized version, generalized form. First of all, finite difference relaxation method adopts a global perspective. That is, it tries to get the solution all over the domain at once. Okay, and from this point to this point, everywhere it tries to adjust the solution together. Not like shooting method, in which we try to build the solution from this end towards that end. Okay, here in the global perspective, all the parts of the domain are given due importance, and they are adjusted all together. Okay, now one more issue. When we try to frame this equation using this derivative function here, then for developing these derivatives or the Jacobian thereof, we will need the values of xi, xi minus 1, yi, yi minus 1, and so on, right? And therefore, to begin with, even at the very beginning of the solution, we need to assume one solution from this end to that end. That may be wrong, in general that will be wrong, but then one set of values for y at every point of the grid is necessary to start the system, okay, start the solution process. Okay. So, what we do? We discretize the domain A B with a grid of points x0 to xn. N was taken as 8 in this example, right? Then function values at xi will mean n into capital N plus 1 unknowns. Capital N plus 1, because capital N plus 1 points are there, into n, which is the dimension of y. Now, we will replace the ordinary differential equations over intervals by finite difference equations, which will look like this, right? And this will give us n into n, small n into capital N scalar equations. That means, capital N vector equations at so many intervals, and each vector equation will stand for small n scalar equations component wise. Now, we will assemble the additional n equations from the boundary conditions, and then this total number of equations will be same as total number of unknowns, and then starting from a guess solution over the grid, we solve this system, and at the end of the process we will get the complete solution. So, this method is called the relaxation method, which works based on the finite difference equations. There is also a finite element method, which is much larger than this course will allow us to discuss. In that, we do not consider finite differences like this, but we try to split the entire domain into small elements, finite elements, and we try to propose the type of functions with appropriate continuity requirements across boundaries, and then the details of those functions we try to work out through iterations, through the numerical methods. So, finite element methods constitute a full course in itself, and so we do not go into the details of that. Towards the end of this course, when we discuss variational calculus, there we will make a small introduction to the basic ideas of finite element methods. And now we go back to the initial value problems and consider a few important and interesting issues in the solution methodologies of initial value problems. In the previous lecture, we discussed methods for solving initial value problems of ordinary differential equations. Now we try to address a few important questions regarding the way the method handles the differential equations. We try to make a stability analysis of the method. Adaptive Runge-Kutta fourth order method or fourth order, fifth order method is an extremely successful method, but its scope is limited. Now, the focus of explicit methods such as Runge-Kutta method is accuracy and efficiency of the method. For the purpose of efficiency, we use adaptation of step sizes. Right now, there is another important issue in the solution process of ordinary differential equation, and that is stability. Stability of the method, not the stability of the dynamic system for which the differential equation is framed. That is another issue which we will discuss much later in the course. Now, stability of the numerical method means that if there is an error at one point, then as the computation progresses, does the error grow or does the error decay? If the error grows, then we say that the process is not stable. Now, the issue of stability is handled in explicit methods quite indirectly through the route of accuracy. Now, if we try to make an analysis of the stability, then let us consider this differential equation, and rather than starting our analysis from RK4 method, that is fourth order method, let us start from Euler's method itself, first order method. The discussion will be simpler. The Euler's method gives us this. From yn, we get yn plus 1 through this relationship, which we saw in the previous lecture. Now, Taylor series of the actual solution around y equal to xn, x equal to xn is this: y at xn, that is the true value of xn, true value of y at xn, plus f evaluated at this correct x and correct y into h plus higher order terms. You see what are the differences here? Here it is yn plus 1, the value of y at x n plus 1 given by Euler's method. This is similarly the value at x equal to xn given by Euler's method, and so on. Here this is the true value, this is the true value, and the function is evaluated at the true point, okay, the true solution of the ODE system. Now, if we try to see the discrepancy between these 2 points, then this difference, that is the value obtained minus the true value, that is the error or discrepancy at x equal to x n plus 1, right, and this is the difference yn minus y at x n, that is the value obtained from the method minus the true value, that is this, plus similarly this minus this. So, f evaluated here minus f evaluated here into h, and then the rest are higher order terms. Now, this is error at nth step, okay, and what is this? Function at x y n and function at x y of x n. This is the evaluated y at x n, this is the true y at x n. Now, from mean value theorem, we know that between y n and y of x n in the y space, there will be a point in the straight line join, in the straight line segment joining this erroneous y and true y. In the straight line segment joining these 2 points, there will be some point at which the derivative of f will be such that this derivative into difference in y values will give this difference of f values that we get from the mean value theorem. So, between yn and y of xn in the straight line join of these 2 points, suppose that point the existence of which is guaranteed by mean value theorem is yn bar. So, at that point yn, we are not making any such discussion for x because x is same at these 2 points. So, at yn bar, then this turns out to be the Jacobian of f with respect to y, the derivative matrix into delta n. Now, if we combine these two and call this matrix as J, the Jacobian matrix, then we will get identity into delta n plus J delta n H, that means I plus H J into delta n plus of course higher order terms. So, you see we get a relationship between the discrepancy at n plus 1th step and the discrepancy at nth step. So, that shows that Euler's step magnifies the error by a factor of this. Now, delta n is a vector, delta n plus 1 is also a vector, error in y at xn, error in y at xn plus 1. Now, this vector is mapped to this vector with this matrix I plus hj, and that will give you the magnification produced in the error as a result of this one step. Now, the question is this magnification of size? Now, we are talking about magnification of vectors. So, if the initial vector is in this direction delta n and the resulting vector is in this direction, then we will be talking about magnification in terms of sizes. Now, is this size magnification size, that is size of magnification, greater than 1 or less than 1? If it is greater than 1, that will mean that the size of the error will keep on increasing. On the other hand, if it is less than 1, then that will mean the size of the error will keep on decreasing. So, using this J loosely as the representative Jacobian. Why we say loosely as the representative Jacobian? Because as we move from one point to another, x will change, y will change, f will change, and therefore, J will also change in general. But as a representative Jacobian, using this same notation J, we can say that from the error at step 1, as we have taken n steps and come to the step n plus 1, then so many times this matrix has been multiplied. Of course, in actual practice, the matrix in between will keep on changing because J is changing, but using the rough Jacobian, this will be the situation. Now, for stability, we need that this error at n plus 1th step goes to 0, that is, it goes on reducing. So, for reducing the error step by step, we will need this matrix to have all its eigenvalues of magnitude less than 1. So, we need eigenvalues of this matrix to fall within the unit circle around the origin. The eigenvalues may be complex, that is why we are talking about the eigenvalues falling within the unit circle around the origin in the complex plane. Okay, that is this. This is the unit circle, and the eigenvalues of this matrix we need their magnitudes we need less than 1. Okay. So, by shift theorem we know that eigenvalues of this matrix are related to the eigenvalues of Hj, because addition of the identity matrix is basically increasing the eigenvalues by 1. Okay. So, if the eigenvalues must fall within the unit circle with the center at origin for I plus Hj, then the eigenvalues of Hj should fall within this circle, which is shifted by 1 unit. This is origin, this is minus 1 0. Okay. So, within this circle, all the eigenvalues of Hj should fall, and that gives us this condition: 1 plus h lambda should be the magnitude of that should be less than 1, which will give this limit on h. That is, now the real part of lambda, if it is negative, then this will be positive, and then it will make sense, that is h is anyway positive. So, then it will make sense, and then the method will be stable, that is, the error will not go on growing, but it will keep on reducing over steps. That is, if lambda is lambda has negative real part and if h is less than this. This is what you will get from this figure also. See this unit circle. If lambda has positive real part, then anyway the eigenvalue cannot fall within this circle. If it has negative real part and h is so small that eigenvalues of h j, that is h lambda, comes within this, then there is a hope that the eigenvalues of h j fall within this and the method is stable. On the other hand, if you take an h step size which is larger, so that the eigenvalues of h j fall somewhere here, then the method will be unstable, because in that case eigenvalues of I plus h j will have sizes which are larger than 1. Okay. So, the same result this you will get if rather than the matrix vector equation system, if you consider a single ODE which is w prime equal to lambda w, allowing lambda to be complex. Now, the way we got this result from the first order method, that is Euler's method, for the second order Runge-Kutta method, we will get a similar relationship in which this matrix will appear, this expression will appear for lambda, which earlier for the Euler's method was 1 plus h lambda. Here it will be a quadratic factor. So, there the region of stability will be that this magnitude must be less than 1, which is this elongated figure. Okay. So, for RK2, that is Runge-Kutta second order method, the eigenvalues of h j, that is h lambda, should fall within this. For fourth order Runge-Kutta method, similarly you can work out the expression of h and lambda, that also will be in the form of an inequality, and when you plot it, you will find that the values of h lambda for stability should lie within this and so on. For higher order methods, there will be similar slight expansions. Still the problem remains that for large zones in the complex plane, the instability problem remains. That is, if the eigenvalues of h lambda fall on this side, then the method is unstable. Even if the values of h lambda fall on this side, but depending upon the value of h, if they fall outside this figure here, then also the method is unstable. That means for unstable differential equations for which the matrix J has eigenvalues with positive real part, the method is anyway unstable, and if the differential equation is stable, that is eigenvalues have negative real parts, but if the value of h is large, so that the eigenvalues fall here, the method is still unstable. So, then how does the step size adaptation of Runge-Kutta fourth order method operate on this kind of a system? As we discussed earlier, the issue of stability in RK4 or such explicit schemes is handled indirectly. That is, as the error grows up step by step, then after a few steps it is identified that the error growth has been too much, and that will be identified through the comparison of two estimates, as we discussed earlier. Through the comparison of two estimates, it will be found that at the 7th step, say, the error is too much. That means over this interval we cannot use a single step, we will subdivide it into two steps, and then any eigenvalue which was found here, that will be drawn inside like this, and it will be found that now it is fine. The error is out of two estimates, the error estimate will show that error is not too much and error is fine. But slowly, because of the stepwise magnification of the error, after a point again the error will grow too much, and then due to the error growth the step size adaptation will be performed, and this goes on, and finally after quite a few iterations, quite a few steps, the adaptation will be taking place so frequently that you will have extremely small steps, but then the errors will be quite large. This is the problem of explicit steps, explicit methods. So, step size adaptation tackles instability by its symptom. It does not handle the actual malady. What will happen if we do not use an explicit method, but use an implicit method. What it means? It means that rather than writing the differential equation in terms of the derivative dy by dx at x n y n, we could write it in terms of x n plus 1 y n plus 1 at the other end of the small interval. That is, rather than taking the slope from here, if we say that what about taking the slope at the point where we would finally reach at that point. The question is that where we will finally reach, that is y n plus 1, we do not know now. So, that means that here we do not get an expression for the unknown y n plus 1, but we get a system of equations in y n plus 1. So, question is, we still have n equations in n unknowns. Okay. So, we can solve it by Newton-Raphson iteration or whatever, but first we ask the question, is it worth solving it? That is, the problem of instability, will that be addressed if we solve this and accordingly find y n plus 1. So, let us first try to see whether it is worth solving this in order to evaluate y n plus 1. So, for that we try to make a similar analysis. What is the discrepancy at x n plus 1 if we use this kind of a formula? That will be y n plus 1 minus the true value. Okay. That will be y n minus y x n plus h into the function value, right, the same equation which we used earlier. Okay. Except that now this f is evaluated at x n plus 1 y n plus 1 rather than x n y n. Okay. Similarly here, and that will give us, this is delta n and this will be h j. This j is slightly different from that earlier j, but still it is the Jacobian matrix at a representative point into change in y, difference in y. Now, notice that earlier in the explicit scheme we got delta n plus 1 is equal to delta n plus h j delta n. Now, here we are getting delta n plus h j delta n plus 1. So, in order to express delta n plus 1 in terms of delta n, what we do? We take this on the other side and then we get I minus h j here, right, identity into delta n plus 1 minus h j delta n plus 1. So, I minus h j inverted and pre-multiplied here will give us this. Now, this is the difference here. Now, for stability of the method, we need delta to decrease over steps. That is, compared to delta n, we want delta n plus 1 to be less. That means, the eigenvalues of this matrix, the inverse of I minus h j, we want to fall within the unit circle. We want the eigenvalues of I minus h j inverse to be within this. Okay. So, for that, suppose the eigenvalue is here. So, for I minus h j inverse, eigenvalue of I minus h j inverse. So, for the eigenvalue to fall here for I minus h j inverse, where should be the eigenvalue of I minus h j? That will be reflection, right? Reflection first by this circle and then by the real axis. Here. So, if it is a plus I b, then its inverse will be 1 by a plus I b, that means a minus I b divided by a square plus b square. This conjugacy is equivalent to reflection by the real axis, and this division is equivalent to reflection by this circle here. That means, the eigenvalues of I minus h j should fall outside the unit circle, okay, outside the unit circle, eigenvalues of I minus h j, and that means that eigenvalues of h j should be again accordingly shifted. Okay. So, if we analyze that, that is, eigenvalues of I minus h j should fall outside the unit circle, okay, and that will give us the limitation on h as greater than this. Now, if lambda has positive real part, then h larger than this quantity will be required for stability. And if lambda has negative real part, then this is always true because H is positive, and then that means it will be always stable. So that means we get absolute stability for a stable ODE system, that is this. I minus Hj having eigenvalues outside this unit circle will mean that Hj must have eigenvalues shifted, I mean outside the shifted circle like this, that is this. So if H falls Hj, if eigenvalues of Hj fall within this circle, then the method will be unstable. For all the rest of the domain on the complex plane, the method is absolutely stable. So this is the advantage of the backward Euler's method. Now we come back to this question: should we solve this, and if so, how? Now, since we know that the stability issue will be guaranteed, okay, then we know that it is worth solving this system to find out yn plus 1, because we are using the slope function at the other unknown end of the interval rather than the known end. So we get this system of equations in the unknown yn plus 1. So we need to solve that. So for solving that, what we need? We need yn minus yn plus 1 minus yn. Okay, that is this. That is the differential equation. We write it, and this is a system of equations in yn plus 1. So we need to solve g of yn plus 1, that is this expression, equal to 0 for yn plus 1. Newton iteration will be this, that is value at step k plus 1 is equal to value at step k into I minus Hj inverse, because its Jacobian of this function will be minus I plus Hj, right? That means Hj minus 1. So in the Newton step you have yk minus Jacobian inverse. So that flip in sign has been taken care of here, that minus has become plus. So minus I plus Hj has become I minus Hj. Okay. So I minus Hj inverse into the difference of the function values, right? So you have got this, the error value at kth iteration. So that is this whole thing evaluated at the kth iteration, that is this. Now this is an iterative method, iterative step. Now in a semi implicit Euler's method, what we say is that anyway we will use the guess value for this Newton-Raphson step at the as the value of yn, the previous value that is known, at x equal to xn. So if we use that as the guess value here and here, then the first step in the Newton-Raphson iteration that you will get will have yn here. Okay. So that is same as this, so this goes off, and yn here. So the function will be evaluated at xn plus 1, but yn which is known. So the function is evaluated here, and this is the first iteration of the Newton's method. Now if you utilize only the first iteration, then what you get is called semi implicit Euler's method. Otherwise the complete implicit Euler's method will require you to have this iteration till convergence. Now similar iterative schemes, similar implicit schemes can be developed for second order Runge-Kutta method also. Now these implicit schemes will have the advantage that stability will be guaranteed, but the accuracy is another matter which has to be handled separately. Now in the next lecture, in the beginning, we will consider what is called stiff differential equations and see how the application of implicit method helps in handling stiff differential equations. And further, in the next lecture, after discussing stiff differential equations, we will raise more fundamental questions regarding the validity of solutions of initial value problems in a physical and practical sense, and from that we will develop some deep mathematical results which will give us confidence to use the solution of initial value problems as we solve in the typical problems. So these two issues we will discuss in the next lecture. Thank you.